Well, it is hot here. I was just about to start recording a video and explain how hot it is, but my dad got in touch asking for air conditioning opinions. So that's how hot it is here. Probably not going to be in the workshop this weekend. It's just too hot to be shut in a small room in PPE. So it's a chance to catch up on a bit of a backlog of editing, I guess, and just to chill as well, in every sense. I was making a project with a jog wheel on it, and my son asked me what the jog wheel could be made to do. And I said, just about anything. It's only software. And he asked if it could be used to dim the lights in his bedroom, which turned out to be a really interesting question. And the answer is yes. But how we got there is pretty interesting. So I'm going to show some stuff here. I set out being reasonably convinced we could do this, but I wanted to do it in such a way that he could participate, because often I just deliver something to him and he'd shown an interest, and I wondered whether it'd be possible for him to have some agency in this process. So that determines some of the decisions I made. This project implements a physical rotary dimmer to control some Bluetooth mesh smart lights. Specifically, they are BR mesh, that's the Bluetooth protocol being used. This particular model of light, there's some Dustek downlighters from Screwfix, and these are not designed to interact with home automation particularly. They're a closed system. And this is going to be a physical device rather than a phone or voice controlled device. My son's already got an app where he can change the RGB values and the brightness, but he sometimes just wants a physical switch to turn them down. So this needs to be reliable and tactile, and it needs to be usable for my son day to day. My son's a teenager, I should say that. He's not like a child anymore. But potentially something he can hack on. So the solution I've gone for is to use the really excellent ESP Home project for this. I'm using an ESP32 based controller, and I picked up two boards, both from Adafruit, an A&O rotary controller, which is like, if you're old enough to remember the early iPods, they had a clicky scroll wheel on the front, before they went to the touch ones, they had actual rotary wheel. This, I think, is a modern design of one of those. And that connects to a Adafruit Feather ESP32 S2, I think it is. It's a standard Adafruit board. Sorry, it's not. It's an ESP32 S3 on a Feather board. And on that, we're going to run the ESP Home with a project or a component called FastCon, which has already been written to send out BR Mesh advertising packets. So all we have to do is connect all of this existing hardware to existing software, set it up for our network, and we should be off to the races. One of the reasons I went for the Adafruit Feather is that you can get it with a Stemma QT/quick connector on it, and as you can for the rotary encoder breakout with its nice plastic wheel. That also has a Stemma QT socket on it. So in theory, you can just plug the two things together without any soldering, which is nice. It means you have more flexibility in the assembly, and it's one more thing that my son could do that wouldn't require my assistance. So in theory, you just need a 4-pin JST SH 1mm cable, and that carries an I2C signal across from the board. There's no soldering, there's no pull-ups, there's no level shifting required. It should be super simple. And then there's the software stack to put on there. So we've got an ESP Home for the firmware components, ESP Home FastCon component to emit the BR Mesh compatible BLE advertising commands, and then optionally we could integrate it with the Home Assistant if we wanted. So the first problem I had with this is that the Adafruit Feather is very much designed to be used with the Adafruit firmware. Specifically, the Stemma QT connectors use pins that are also boot pins. So there's a hack in their firmware hack. They have something in their firmware that ignores those pin statuses on boot until after it's booted, and then the pins are used not for boot but for supplying the data to the Stemma QT connector. So if you put ESP Home on as the firmware and then connect something to the Stemma QT sockets on the board, it won't boot, and you spend a long time trying to figure out why it won't boot. In fact, there's a helpful error message, and if you find the right logs, it tells you that the GPIO pin 3 and 4 are strapping pins, boot strapping pins, and you shouldn't connect anything to them at boot time. Since the socket is permanently wired to those pins, there's really no choice. And that means that you can't use an Adafruit Feather QT connector with ESP Home on this board. So that put us, it meant we couldn't just plug the two things together with a JST cable. We had to go back to soldering anyway. So I soldered it up. It's only 4 lines. It wasn't a big deal, but it means they're now, it now needs to be mounted because it's got these fragile solder connections to deal with. But we got there. We got the thing booting. ESP Home is a configurator-based system that's pretty interesting. And what I mean by that is you put your properties into a YAML file, and then there's a preprocessor that processes that YAML and turns it into probably C++ behind the scenes, and then it uses other properties in that YAML to work out what your toolchain should be for your specific board, and then it compiles that C++ ready to push onto the firmware of your board. And that makes it a good choice for my son, because it means that once I've got it set up and working and compiling and flashing to the board, he can still tinker with things inside that toolchain fairly easily and even over the air flash it. There are magic values to figure out. You've got to figure out the right settings for your particular board and any exclusions you need from the default setup. You've got to put your secrets file in there. But once you've figured those out, that's a one-time deal. As I say, there was a bit of messing about with figuring out the right pins to use to avoid the boot pins and soldering on the components to those and getting those to work. And then I had to use an external component called Seesaw to read the A&O rotation values. But once that's in place and you define the various buttons and the rotary control as a sort of sensor inside your thing, you can then append scripts to them. So you can set default values. You can kind of say, I want you to set these things on this button press. That my son is kind of familiar with from his experience with other more basic programming languages, things like Scratch and stuff. And then the most complicated one is for the scroll wheel, where we actually wrote a bit of C++ Lambda to allow it to step values up and down. And I walked my son through that so he knew where to make changes if he wanted to tinker with that. Now, one thing that is required is a secret key for the mesh lights. The way the BR mesh system works, it sends out these advertising packets. The controller sends out advertising packets, and they're encrypted with a secret key. And any device that knows that secret key, and only devices that know that secret key, can decode those packages and do whatever it says. It's kind of a read-only system where the controller just throws out packages, and devices that can understand that react to it. But in order to make the lights listen to our controller, we need to know the secret key that's already encoded into them. And that was defined at the time my son set up the system originally on his smartphone app. So we needed to get the value from the smartphone. I figured that you must be able to add second smartphones or move the admin from one smartphone to another. And sure enough, within the software itself, the BR Mesh software on my son's phone, there was the ability to display a big QR code that encodes a lot of data. And I could scan that on my phone, and I could either transfer control or add a second control device to the system. I did look at whether we could extract the secret key from that QR code, because it must be in there in order for my device to send these encrypted packages as well. But that's also encrypted with a different key that's not available. So a bit of reading around, and it showed somebody else had already solved this problem for us, so we could simply follow their route, which is to use Android Debugger. Okay, well that was interesting. My camera overheated, which is a known fault in this model, but we'll carry on from where we were. Trying to get the secret key to be able to talk to our BR Mesh lights using Android debugging. So you connect my mobile to my laptop, approve its fingerprints, and then you can use the ADB, the Android debugger commands, to look at all the logs coming off of the phone. So you start logging to a file and then open the BR Mesh app on the phone and send some signals out to the lights, and the app logs into the Android logs, which we're viewing from the laptop. And because of a handy security flaw in the Android apps, you can see the secret key in plain text in the log file. So I've starred mine out here, but this get payload with inner retry would normally contain the plain text for the secret key. So now we have our secret key. We can add it to our secrets file for our ESP home program. We can compile that up and we can talk to some lights. Okay, so this is an on-location update. We are venturing into the room of my teenage son here in the perpetual darkness. Down here, we'll find, it's quite hard to see at the minute because it's black in the dark. It's just powered by USB-C. This is the dimmer box. So in theory, I should press this and it will generate a Bluetooth advertising packet to turn the lights on. Doesn't make a huge amount of difference because up there they're pretty dim. But the tracker wheel here allows us to dial up that and they get a lot brighter. And then the buttons on the outside select his presets. I'm not sure how well these differences will come through on camera. That was pretty significant. And he can dial them back down as well. All right, final thoughts then. So this was technically quite a simple project. 2 off-the-shelf boards soldered together. ESP Home, which is a great open source project. The FastCon, which is designed for the BR Mesh protocol. Didn't have to write that, so that's great as well. And the configurator, which meant it was good because once I'd ported the toolchain, which could all go into Git, onto my son's laptop, he was able to then tinker with the values and recompile and flash over the air. So I don't think configurators are always the right solution. It was pretty tricky finding the correct values to get the toolchain to work for the particular hardware that we were using and the particular devices we were plugging into it. But once the magic values were in place, it's easy for my son to then make small changes. You know, he can tweak some of the numerical values in the files. He can change the behavior of the various controls, and none of that impacts the wider ecosystem of the toolchain. So for that, it's very good. It's a very good use case for that. Thank you for watching. Stay cool.